Displacement current. What is displacement current? So suppose we have the plates of capacitor. And it is connected by some kind of variable voltage. So it is connected with some kinds of variable voltage. So what it will take place, you notice that, so these are the plates. So if we apply Ampere's circuital law here at this position, so if we take a loop, so eventually we will get magnetic field around it. We will get magnetic field here. That's because current is moving inside either in this direction or this direction. But the current is actually variable, so this magnetic field will also vary. Okay. So this is according to Ampere's circuital law. So this is okay. But you notice that if we place a loop here, so here we have no wire. This is a plate and this is a plate. So in between nothing is there. We can say it is space, or we can say air is there. So air can be considered as more or less it is like space, because it also happens if it is space. So it will also take place. So he noticed that here also we are getting some sort of magnetic field. So we are getting magnetic field. But what is passing through this? No current is passing through this loop. Only electric field is passing through this loop. That means this variable electric field can also create magnetic field. So how the calculation will come? So we can say, okay, so suppose this is a plate having total charge Q. So total charge Q, and its area of this loop. So this area, this much of area. So this area is A. This much area is A. So this variable electric field is producing magnetic field. That means there is something wrong in Ampere's circuital law. It is proposed, not proposed by me, it is proposed by Maxwell. Into dl. So if we take the line integral of this, so that is equal to mu naught into current enclosed. Okay. So this is Ampere's circuital law. So this electric flux is equal to electric field into area. Now this electric field, so this is sigma by, and this sigma is the charge density in capacitor plate. So this sigma can further be written as, so we know that electric field equal to sigma by epsilon naught in space, and sigma is equal to charge by area. So we can write like this, charge into yes, charge by area. So what we can write here, that sigma in place of sigma, we can write is Q by so it is getting cancelled. And as because we are getting current and this electric flux, so this electric flux is basically variable, because the source we are applying is also variable, so it is differentiable. Because the flux is variable, it is varying with time, so it is differentiable. So if we differentiate this quantity with respect to time, then we will get 1 by epsilon naught and dq by dt. So this dq by dt, this is basically producing a current. dq by dt is producing a current. So this current is called a displacement current. So this we can write. So this is called displacement current, this quantity. Now why this Q is varying? Because the Q is variable if the electric flux is variable. Now why this flux is variable? Because electric field is variable. Now what is electric field? Electric field is this, sigma by epsilon naught. And what is sigma? This is charge by area of the loop. Whatever the area of the loop you take. You can take any area of the loop. So this is that area. So it is cancelling and ultimately it is giving a displacement current. So what we can write here, epsilon naught multiplied here, okay, so this is the displacement current. Is basically not only mu naught into I enclosed, but also displacement current. Now what is this displacement current? So this is mu naught, and we have seen this is epsilon naught. Now in space, this thing is not present. That means no conduction current is present. We can say this is conduction current and this one is displacement current. At any instant, these two are same for any system where there is wire and there is space. But if there is only space, then this thing will not be present. So if this is absent, so we can write this is only equal to so this is basically one of the equation that Maxwell has given. So this is one of the equations that Maxwell has given, and the other equations are like this. This loop of area A, and this magnetic field is a function of time. Magnetic field is a function of time, means it is a variable magnetic field. Then you can say that this magnetic flux is produced, that is equal to B into A. This is the magnetic flux. But if we take the differentiation of these, so these will basically produce EMF minus d phi by dt, so that is equal to EMF. So this is Faraday's law. So now it is producing EMF. Now if someone asks what will be the electric field, what will be the electric field on its circumference, then what we can do? So this is the EMF. So we can consider that this loop is made up of several small batteries like this, very small, innumerous batteries. It is made up of innumerous batteries. So that's why it is producing an overall EMF. So this is the thing. Now what will be the field? So the field produced in this loop will be this EMF produced divided by the length of the loop. Okay. So we can say that the electric field produced is EMF by the length of the loop. So length of the loop. Okay. Now electric field is a vector. So electric field is a vector, and this EMF produced can be written as minus d phi b by dt. So this is the EMF produced, and this length, so this length is also a vector. Isn't it? Okay, so what we can write if we take this side, so we can write E dot dl and its integral, so that is equal to minus d by dt and phi b. Now what is this phi b? Phi b is basically the magnetic field into the area of the loop. So the area of the loop can be written as in this way. So minus del by del t of this magnetic field into area. So this magnetic field also is a vector and area is also a vector. So area is also a vector. Okay, let us take this. So this and the integral of this. Ampere's circuital law. So this is B dot dl is equal to displacement current into mu naught. So let us write this del phi e by dt. So this is one, and the second most important is E dot dl. So what it gives? It gives EMF. This is nothing but this one. So this is one important line integral and this is another important line integral. And on the basis of these two line integral, we can prove the Maxwell's equation of electromagnetic wave. Okay. The electric flux. So electric flux equal to charge enclosed by epsilon naught. So this law is Gauss's law. Gauss law. This is Gauss's law. Okay, this one, Gauss's law. And the second one, if we pass magnetic field through a surface area, you'll get nothing. You'll get some eddy current, you may get some eddy current, but basically, if magnetic field passes through some solid area and magnetic field is passing through this, so what you will get? You will get nothing, you will get some small loops. So these are called eddy current loops. But basically it will have no effect in space. So because in space you will not get any solid area. So that's why these two surface integral will not be used to prove Maxwell's equation. Now watch it. So this is the direction of propagation of the wave. So we do not know what is the velocity, but in this direction the wave is basically propagating. And Ey, so y is the direction of electric field and we have considered that z is the direction of the magnetic field. So first we will use this equation. So first of all we are going to use this equation. Okay. So E dot dl. Now this is line integral. So see. So line integral means we have to take only this line. So electric field is along y-axis. So this is the line. So its length is delta y. Okay. So delta y, but it is moving upward. Okay. And then this one is also delta y. So the length is delta y. But delta y upward. So the electric field is moving upward. Simultaneously the magnetic field is moving along z, and we know that the direction is electric field cross magnetic field, so this is the direction of the wave. Okay, so now delta y, this one is equal to this one. Now again, how will we take this difference? How should we take this difference? This is delta y, this is delta y. So this has directional property, and what we can write that this electric field, its magnitude is delta y, no doubt in this. Okay, but this delta y, that is actually the electric field, its magnitude is delta y, but it is electric field, so it is electric field at a distance x plus delta x. So it is basically Ey, electric field along y direction, but at a distance x plus delta x. x plus delta x. So here this electric field, first we are taking this one, and now again it is returning back. So when it is returning back, its magnitude, its length is again delta y. So this is delta y. But this electric field is also Ey, y minus, because it is in opposite direction. And it is at a distance of x. So this. Okay. So very simple. The length magnitude is delta y. And it is Ey, electric field at a distance x plus delta x minus means because it is returning. So that is Ey at a distance x. At a distance x. We have taken Ey along positive x-axis. So this one will be negative. So that's why negative Ey at a distance x. So this one is my line integral. So and equal to right hand side. So what we have in the right hand side, you see minus d phi b by dt. So that is equal to minus d by dt. For this type of a electric field loop, the magnetic field will be in z direction. So that's why it is in Bz. So Bz into area, magnetic field into area, that is actually magnetic flux. So the area is delta x into delta y and the magnetic field is Bz. So what we can write, that Bz into the area. So the area is delta x into delta y. Okay. Now again see, when we come with this type of equation, that some function at a distance x plus delta x minus some function at a distance x divided by delta x, then it gives f dash x. So this is basically the first principle. But here what we are getting that Ey, suppose electric field is a function of x. And it is x plus delta x minus Ey at a distance x. So what we can write, we require a delta x at the bottom that we do not have. So we can give one and we can write one here. So this equation will be delta x delta y. So this format will be like this: x plus delta x minus Ey at a distance x by delta x, that is equal to, now see these things are constant, delta x delta y, these are constant, so we are making them out, minus delta x delta y. So del Bz by del t. Okay. Now what we are getting here, this is actually Ey is a function at a distance x plus delta x minus at a distance x divided by delta x. So this is actually, and these two things, delta x delta y are getting cancelled. Y by del x, that is equal to minus so very simply we are getting this one. So Ey is a function at a distance x plus delta x minus Ey at a distance x divided by delta x. So it is just like the first principle. So this is del Ey by del x, differentiation of this function Ey, and here we are getting minus del Bz by del t. So this is one equation that we are getting. Okay. So what we have got here, I am writing this here because we have to use this later on. Magnetic field, now see, as the electric field moves up, so the magnetic field also moves along the direction, because the electric field and magnetic field both are in same phase in electromagnetic wave. Okay. So if electric field moves up, then magnetic field also moves away from the mean position. What is the magnitude? What is the line length of the line? That is delta z. And when it is moving back, so the length is also delta Z. It has a small length parameter. That means it is moving up and then down, but it is not like moving up and down at the same position, but it has a little gap. So it has a little gap. So moving up and down. So we can say this delta x is so small. So magnetic field is also like this. So this delta x is infinitesimally small. Now this b, the magnitude of this line integral will be only delta z. So delta z, its magnitude is delta z. Okay, but it is magnetic field at a distance, again x plus delta x minus magnetic field along z direction. Why minus? Because it is now returning, so we have taken magnetic field along this direction. Okay, now it is moving opposite to the z direction, so that's why minus dz at a distance x. So that is equal to mu naught epsilon naught. Now del by del t of phi e. Now what is phi e? This is the electric flux. Now see, electric flux means this loop. Now the loop is moving like this, isn't it? It is in the plane xz and it is moving like this. So the direction of the electric field will be downward. For this magnetic field loop, the electric field will be downward. So along minus y direction. And we have taken our Ey in positive direction. So what we have to do? No problem. So the magnetic field is downward direction. Electric field is downward direction. So we have to take minus Ey. So we have to take minus Ey and the area. So area is delta x into delta z. So this is the area. So area will be delta x into, because it is electric flux. So delta x into delta z. And why we have taken this minus Ey? Because for this loop, the electric field will be downside of this xz plane, that is towards minus y. But we have actually considered Ey along plus y direction. So that's why we have taken here a minus sign. Nothing but this. Okay, now again here, so this is delta z, and if we give a delta x here, so again it will be divided by delta x. So it will be like bz at a distance x plus delta x minus, now it is not required, minus bz at a distance x whole divided by delta x. So that is equal to mu naught epsilon naught, and this delta x delta z, we can make them out, delta x delta z, and there is a minus sign, so make it out. Okay, and del Ey by dt. So this del z del x del z is cancelled, and we know that this thing will be nothing but del vz by del x, and this will be minus mu naught epsilon naught del Ey by del t. So now this is our second equation. So this is our second equation, and we have got our first equation this. So the first equation is this. So this is the second equation, and the first equation that we have already written here, that is equal to del Ey by del x, that is equal to minus del Vz by del T. So these two are the equations that we have got from this figure. Okay. Now, if we differentiate this first equation, differentiating again with respect to x. So we want to differentiate this equation with respect to x again. So what we will get? We will get del square Ey by del x square equal to minus del square Bz by del T del x. So we have differentiated both sides with respect to x. Now see, in our first equation we have got del Bz by del x. So we have to make some changes here on the right hand side of this equation. What we can do, we can write it like this: del square Ey by del x square. So left hand side intact, and this right hand side can be written as del by del T and del Vz by del x. Why we have taken in this form? Because we already have derived this form, del Vz by del x. So this has a value. So that's why we have taken this partial in this form. Okay. So now we want to change only this portion. So this portion has a value, this minus mu naught epsilon naught, this one. Okay. So putting the value of the second equation here, what you will get? So from here, minus del by del T into, this is minus mu naught Now this minus mu naught epsilon naught will come outside. This is minus, so this will be plus. 1 minute. This del square Ey by del x square equal to plus. So this will be mu naught epsilon naught, and this is del by del T. So this will give you del square Ey by del x square, that is equal to mu naught epsilon naught del square Ey by del T square. Now see, this equation is like the form del square y by del x square equal to 1 by v square del square y by del T square. So this is the normal classical equation of any wave, and for electromagnetic wave it is not any exception. We are getting this equation. Oh my god, so it is very good. That means 1 by v square should be equal to this quantity, mu naught epsilon naught. So 1 by v square equal to should be mu naught epsilon naught. So what we are getting, 1 by v square, that is equal to mu naught epsilon naught. So the value of v equal to 1 by root under mu naught epsilon naught. And if we check this both dimensionally and by magnitude, what we get, that this v becomes c. Okay. So that's why what we can say, that electromagnetic wave has speed that of light in vacuum. So this is basically the proof of Maxwell.